Hello everyone, welcome to EEEE lecture number 9. Today we are going to start with a new theorem that is called as maximum power transfer theorem. So first we will see the statement. So maximum power transfer theorem says that in a DC circuit, maximum power is transferred from a source to the load when the load resistance RL is made equal to the equivalent resistance of the network viewed from the load terminal, that is RTH. Alright. So let's say that we are doing the conversion for Thevenin's theorem. So any complex network can be replaced by a single voltage source with a in series with a single resistance RTH. So this RTH, when it is equal to RL, then the maximum power from the source, that is VTH, will be transferred to the output. Alright. So over here, this is my source and this is my load. Alright. So in a DC circuit, maximum power will be transferred when VTH will be equal to RL. Alright. So maximum power will be transferred from the source to the load when RL is made equal to RTH, Thevenin's resistance. Now we'll go for the proof that this really happens. Maximum power is transferred when your value of RL is made equal to RTH. So let us see that how it happens. So from this network, if we calculate IL will be given by VTH upon RTH plus RL. So that is what we have written over here. Power across RL, load raised to RL, will be I square R. So that will be IL square RL. IL is VTH upon RTH plus RL. So it will be VTH square upon RTH plus RL the whole square into RL. Alright. So the numerator is VTH square RL, that we term as U. Okay. And the denominator is RTH plus RL the whole square, that we term it, then we denote it as V. Alright. So from equation number 1, RTH and VTH are constants. Alright. But therefore the power depends upon the load RL. Alright. So to find the maximum power P max, we need to differentiate equation number 1 with respect to RL. So this is my equation number 1. Let me see if I can rewrite it. Yeah. So let me rewrite equation number 1. Power across RL will be equal to VTH square, right? Yeah. VTH square RL divided by RTH plus RL the whole square. So this is my equation number 1. This, let's call it equation number 1. So consider this quantity as numerator quantity as U and denominator quantity as V. Alright, so we differentiate this equation number 1 with respect to RL, keeping VTH and RTH constant, and we set the result equal to 0. So for maximum power P max, dP by dRL or dPRL by dRL will be equal to 0. So it will be differentiation of derivatives by division. So let's say d by dx of u by v will be v du by dx minus u dv by dx upon v square. Alright. So in our case, u is vth square rl and v is rl plus rth square. So dp by drl will be, first of all, v will come. V is rl plus rth the whole square. Then du by dx. So here will be du by dx. So it will be here this differentiate with respect to RL will be how much? VTH square. So VTH square comes. Now here minus VTH square RL, that is U, into dV by dx. So this, if you differentiate, you will get twice RL plus RTH. So that is what we got over here, divided by V square. So V is RTH upon plus RL the whole square, that raised to square. So RTH plus RL raised to 4, that is equal to 0. So when we equate it to 0, your left hand side of 0 will remain as it is, because this goes over there and becomes 0. So now we rearrange the terms. We take VTH square common. So we got VTH square into RL plus RTH is equal to into RTH plus RL minus twice RL is equal to 0. So that is what we get. So from here we get RTH plus RL minus twice RL is equal to 0. So RTH is equal to RL. So this proves that this proves the maximum power transfer theorem, that when the Thevenin's resistance is equal to the load resistance, only then the maximum power will be transferred. And what is the power given by VTH square RL upon RTH plus RL square? Now at maximum power RL is equal to RTH. So we substitute wherever there is RL as RTH. So Pmax will be equal to VTH square into RTH divided by twice RTH the whole square. So here if we simplify further, we'll get VTH square upon 4 RTH. So Pmax will be given by the maximum power. This is the maximum power. The maximum power will be given by VTH square upon 4 RTH. Alright. So let's revise what we have done so far. So any complex network, okay, we have a complex circuit. We have at the output terminals A and B, and here we connect the load RL. This gets converted with the application of Thevenin's theorem into a single voltage source, Thevenin's voltage, in series with a resistance RTH. All right, this is terminal A and B, and we connect back the load resistor. So what the maximum power transfer theorem says is maximum power will be transferred from the source to the load when RL is equal to RTH. Alright. Then maximum power will be transferred from the source to the load. Then what is the maximum power given by? Maximum power is given by VTH square upon 4 RTH. Is that what we got? Yeah. VTH square upon 4 RTH. So these are the two formulas which you should remember. And this is the summary of maximum power transfer theorem. Maximum power transfer theorem. Now what we need to do is we'll directly start solve a numerical and we'll analyze the circuit further. Alright, so let's do that. So let's write numerical number 1. So numerical number 1 says that, let us draw the numerical. Yeah. So we have this circuit that the question is find the value of RL and also find maximum power for the circuit shown. So let's draw the circuit now. So this is my circuit. I have 5 ohm resistance. Then I have 10 volt supply. Over here I have a 6 ampere current source. Then I have 2 ohm resistance. Here I have 3 ohm resistance. Here is my RL. Value is not given. We have to find that value. And here we have 4 ohm resistance. Alright. So basically that is what we need to do. We need to find out the maximum power. So this point is over here is my A and B. Okay, so we have to do the as we do the normal Thevenin's theorem, and at the end we'll substitute that RL is equal to RTH and calculate the maximum power for the circuit. So let us begin. We have to follow the same approach as we followed for Thevenin's theorem. Okay, only at the last step we'll do it differently. So let me write it in summary what we need to do first. So let's start writing the solution. Okay, let me adjust the pen. Yeah. So let us start writing the solution. So we have over here find. We need to first find RTH. Then say that maximum power will be transferred when RL is equal to RTH. So that's the second thing. Then measure or find VTH, calculate VTH, and finally you calculate the maximum power which will be VTH square upon 4 RTH. So that's the procedure. First you find RTH, then you equate RL equal to RTH, then you find VTH, and finally you find the maximum power. So this is the flow we will follow. Now let us start with RTH. So let's start. So the first point is calculate Thevenin's resistance RTH. So what is the procedure over here? The procedure is very simple. We need to remove RL, and secondly deactivate all sources or replace all sources with their internal resistance. Deactivate all sources. All right, so let's draw the circuit again by deactivating all sources. So here we have 5 ohm. Here we have a voltage source, so short circuit. Then current source will be open circuit. Then we have a resistance of 2 ohms. Let me write the value over here. This is 5, this is 2 ohms, and then we have a resistor over here of value 3 ohms, and here we have a resistor over here of value 4 ohms. These are points A and B, terminals A and B. Alright, so next we need to calculate RAB across the terminals A and B over here. So how do we do that? If you see carefully over here, this is open circuit. So this 5 ohm resistance is in parallel with 2 ohm resistance. So 5 ohm parallel to 2 ohm will give you the answer as 1.428 ohms. Alright. So if you can work it out over here, now we draw the circuit again. So we have 1.428 ohms. Then we have over here 3 ohms, and we have over here 4 ohms. Okay, this is A and B, and now need to find RAB. So if you see carefully, RAB is series combination of these three resistances. So RAB will be equal to 3 ohm plus 1.428 plus 4 ohm, and that comes out to be RAB is equal to RTH, which is equal to 8.43 ohms. So that is the answer. The Thevenin's resistance is 8.43 ohms. Now we will write a statement that maximum power, max power, is transferred from source to the load when RL is equal to RTH, which is equal to 8.43 ohms. Okay, so maximum power will be transferred when RL is equal to 8.43. So we got the value of load resistance as 8.43. Now the next task is to calculate VTH, Thevenin's voltage. So let's do that, or calculate VTH. So what's the procedure to calculate VTH? Very simple. First, remove RL and find the open circuit voltage, OC, open circuit voltage between A and B terminals. Okay, that is called as VOC or VAB, or it is VTH, Thevenin's voltage. So what we will do is, we'll see the circuit again. We'll just remove RL, load resistor RL, and we measure the open circuit voltage between the points A and B. Alright, so let's continue further. Let me draw the circuit in this condition. So I'm redrawing the circuit, but um, without the load resistance. So here we have 5 ohm resistance. Then we have over here 10 volt. Here we have a current source of value 6 amperes. Here we have 2 ohm. Here there are terminals A and B. This is 4 ohm and this is 3 ohm. So we need to calculate VAB or VTH or VOC, open circuit voltage between terminals A and B. So if I highlight this part, you always start from B and then you go to A. Alright. So basically, if the current in this loop, let's say the current in this loop is I1 and current in this loop is I2. So now what will be VAB? VAB will be actually, in reality, VAB will be this. There is no current flowing through this 4 ohm and 3 ohm because it is open circuit, but current is flowing through this 2 ohm. So when you go from B towards A, it is in the opposite direction to the current. So it will be 2 ohms into current I2. So that is what is VAB. We need to find the value of I2. So we need to apply mesh analysis over here. Now if you apply mesh analysis over here, one thing is clear. We have a super mesh scenario because 6 ampere current source is set between mesh number 1 and mesh number 2. Alright. So we need to apply super mesh. So this is my super mesh. I'm marking green in color. Alright. So what is the equation relating to super mesh? So we have over here um, I2 minus I1 is equal to 6 amperes. This we call it equation number 1. So this is the the relation between the current source and the two currents in two meshes, one mesh 1 and mesh 2. Now we apply KVL to super mesh. Okay, so what do we get over here? This is rise in potential, so 10 minus 5 I1, then we go over here, it will be minus 2 I2 is equal to 0. Alright, we arrange this as minus 5 I1 minus 2 I2 is equal to minus 10. This is equation number 2. Now in equation number 1 and 2 there are two unknowns and two equations, so we'll put it in the matrix form. So this is I1 I2, and this will be I1 amplitude is minus 1, a coefficient, and I2 is 1. Here it is minus 5 and minus 2. This will be 6 and this will be minus 10. So if you work this out carefully, you will get the answer of I1 as, so I1 is coming out to be minus 0.28. Okay, sorry, so this will be 0.28 minus 0.28 amperes, and current I2 will be 5.71 amperes. Alright, so here we know that VAB is coming out to be 2 into I2, so we'll calculate VAB. VAB is I2, which is 5.71 into 2, which is coming out to be 11.42. So we got the answer of VTH, which is 11.42, that is equal to VTH, and this is the Thevenin's voltage. So we have found out the Thevenin's resistance and Thevenin's voltage. Now next step, we draw the Thevenin's equivalent circuit. So let's draw the Thevenin's equivalent circuit. This is VTH, RTH, this is A and B terminals, and we connect back your load RL. Alright, so over here this value over here is, let me write it, this is 11.42, this is 8.43 ohms, and RL is 8.43 ohms. So what is the maximum power? Maximum power will be transferred when RL is equal to RTH, and its formula is given by VTH square upon 4 RTH. So Pmax will be 11.42 square divided by, let me write it properly, 11.42 square divided by 4 times 8.43. Alright, so if you work it out, your Pmax is coming out to be 3.86 watt, and that is the answer. Okay, so now let us check these results in LTspice. So I'll go to LTspice window. Let me go to LTspice window. Alright, and let me keep this window open over here. So first we will measure RTH. So RTH will be measured using this diagram over here. So let me add the resistors. So there are two resistors over here, and there are two other resistors over here. Let me connect them with the wire quickly. Now remember, there is no ammeter in or no ohm meter in LTspice. So we will use a voltage source and measure the value. Divide by the current flowing to that voltage source will give us the resistance. So this will be 2 ohm. This is around 5 volt. This is 3. This will be 4. And these are points A and B. So I'll highlight it as A, and this will be B. Alright, now in order to calculate RTH, we have to connect a test source of voltage, let's say 10 volt. And let's see how much is the current drawn in the circuit by this voltage source. So let me connect it. Yeah, and the value is around 10 volt. Now I need to connect the ground also. Let me connect the ground over here, and I connect it with the wire. Now I'll simulate it. Ground was required. I'll get simulate select DC operating point and click on OK. So don't worry, the current coming out of the voltage source in LTspice is considered to be negative. So I of R1 is 1.1644. So I'll divide 10 divided by 1.18644 is coming out to be 8.428. Okay, 8.428. That is very close to 8.43. So that is what we get. Let me add that number and copy that thing, and let me show you how you got this again. So I'll right click over here, go to draft, go to comments, I added this. Then in the next statement I'll write RTH will be equal to V1 divided by current flowing through V1, and that will be 10 volt divided by 1.18644, and that is coming out to be let me check it again. Okay, the answer is coming out to be 8.4428 volts ohms. All right, so this is the value of the Thevenin's resistance. RTH theoretically, I mean, in LTspice simulation, we are getting 8.428, and by theoretical value, we are getting 8.43. Now, let us calculate VAB. This is the circuit for VAB. So I'll remove this voltage source, and there will be a current source between these two, resistors. So let me connect it over here, and there will be another voltage source between this. So let me, delete this part and add a current and a voltage source. So this is my current source. I'll change the direction over here, and then also I require a voltage source connected over here, and at the top I'll connect a resistor. Now my circuit is almost complete. Let me connect this components. Yeah. All right. So now let me keep it over here. So this value is 5 ohms. This voltage source is 10 volt. This current source is 6 ampere. And this is the VAB, voltage across A and B. We need to find out the value. So let's simulate it. Click on run, simulate. We are getting VA as 11.4286 and VB as 0. So VAB is how much? 11.42. We are getting it theoretically, and practically we are getting in simulation 11.4286. So that's fine. And also we need to find the maximum power through the load, right? So for that, let's say I'll make the original circuit and I'll put the resistor back. So there I can calculate the maximum power. So here I put the resistor back. Now the resistor value is how much I got. I'll substitute as 8.428. All right. So that's the resistor value. Now in order to find the power, we need to simulate the circuit. Okay, and place my cursor over here near R5. I guess I'll get the value over here. Okay, so current flowing through my resistor R5 will be how much? Need not require that. I require directly the power. So let me show you the power. If I place my cursor over here, it will give me the power. If you can you see the power dissipation at the bottom of the screen? Dissipation is 3.874, and we are getting it theoretically as 3.86. So that is quite close. That is the power flowing through the load resistance marked as R5. That's fine. All right. And the power is coming out to be 3.874, and theoretically it's 3.86. All right. So yeah, that's all for today. Next time we'll solve another numerical on maximum power transfer theorem. Until then, have a good day and thank you.